Okay, now, somewhat related to the diagrams that we have drawn, we're going to talk about the mathematics that help us figure out what the activation energy is. Now, this all involves rate constants, like we found with the first order rate constant. This is one of the ways that we do this, and from that we're able to figure out what the activation energy is going to be. So I'm going to show you the derivation of where the equation came from, and then we're going to do a couple practice problems related to that. Now, the guy who came up with this idea is Arrhenius. So this is the same Arrhenius that you may or may not remember because it was during the haze of the COVID when we were out in the spring. But he was famous in developing probably the first definitive acid and base concept. Now, acid, he said, gave off hydrogen ions, and bases gave off hydroxide ions. It was later refined by two sets of scientists after that, but he got the ball rolling. Very intelligent Swedish scientist. Now, what he found in both his experiments and his thoughts following it was that there are really two factors that determine if a reaction is going to occur or not. One is the temperature. Now, as you know, if the temperature is increased, those molecules start going faster, they collide harder, bonds break, dogs and cats living together. Anyway, so we get violent reactions. But just because two molecules collide does not necessarily mean that they will break apart. They have to be colliding in the exact spot that they are weakest. And that's why some things react very quickly and some things do not. Especially in organic chemistry, that happens. So if you ever take organic chemistry in college, you're going to run into that idea quite a bit. So, as he said, temperature and what he called orientation were the two major factors in that. And from that, he surmised that the rate constant, and correctly so, that the rate constant was directly proportional to the rate of reaction. The higher the rate constant, the faster the reaction is going to go. And so that's why we spent all that time working with K values in that particular homework problems. Now, so what he found was that he found a fraction of the molecules were going to react using this formula right here. Now, E, if you may or may not know, that is called the natural number found by Euler. And the exponent of E is negative activation energy divided by RT. Now, R is the ideal gas law, but since we're dealing with joules in activation energy, we have to use the joules version of R, which we've never used. And that is 8.31 joules per mole Kelvin. So you'd be using that number now instead of these 0.0821 liter atmospheres over mole Kelvin. But we are still using Kelvin for temperature. All right? So, now, let me show you what he did here. Now, this is how he started here. This is a fraction, and since the fraction is going to be less than 1 because you can't have a set of molecules all of a sudden colliding and creating more things than what they started with. The conservation of law of conservation of mass and matter simply states that what you start with is what you get. We can't create more of it. So his orientation factor that he talked about was this capital A. Now capital A, then he said, you take that orientation factor times the frequency which they are going to collide, and gives us this equation right here, which is really good. The problem is you have to experimentally figure out what capital A is, and he found that to be a tremendous pain. So he developed a process, a mathematical process to get rid of it, and that is by, first of all, knowing that if you have two scenarios, you have K1 is equal to this, and K2 equal to this. He then took the natural log of both of those equations, and this is what we end up with here right now. The reason why there's a plus sign here is because when you Remember, the word logarithm means exponent. The exponent base is e, Euler's number, the natural number. And when you take two numbers that are multiplying together, you're adding their exponents. So when you're turning them into exponents, you're adding the exponential values. And so you got the natural log of a and the natural log of this complex right here. And the beauty of that is that the natural log, and we subtract these two, the natural log of a minus the natural log of a just cancels out, it's zero. In this case right here, we got the natural log of k1 minus the natural log of k2, and then the natural log of e. Now remember, natural log means the exponent of e. Well, the exponent of e is negative EA over RT1, so that goes there. And for this one, it's negative EA over RT2, and we're subtracting them, so that should be a subtraction symbol right there. Now, when you subtract two exponents, you are dividing by their like base. These both have a like base of e, and so you take k1 divided by k2 when you subtract the exponents. Over here, we factor out an EA over R from both of these terms. And it left us a negative 1 over T1 here, because that's all gone, but that's in the denominator. Minus a negative is the same as plus a positive, and the EA over R is yanked out over here. That leaves us 1 over T2. Not squared, sub 2. So this is the first temperature, this is the second temperature. Generally, you don't like to put negative values in a parenthesis in math like this, so we switch the order around, and instead of saying 1 over T1, 1 over T2, which is kind of clumsy, we use the exponents t to the negative 1, t to the negative 2. So we end up with natural log k1 over k2 equals EA over R, parenthesis t1 to the negative 1 minus t2 to the negative 2. And I just realized I just did that wrong. It's supposed to be the other way around. This is supposed to be 2. And this is supposed to be 1.